So, hello everyone, welcome back to my YouTube channel. So, today we'll be continuing our subject design and analysis of algorithms. And today we'll be doing the topics dynamic programming, strill algorithms, suffix tree, tries, and the types of problems that is P class problem, NP problem, NP complete, or NP hard. So, let's start. So first of all, we need to memorize this table in order to solve our questions. Whenever we talk about minimum, maximum, or counting ways, optimal solution, we mostly use dynamic programming. When we say substring search in text, we use a string algo. We'll be covering KMP, Rabin-Karp. Then many pattern searches, we use try. Prefix-based queries, we use a try. Longest repeated substring, we use suffix tree or array. Longest repeating subsequence or substring. Dictionary words, we use try. Overlapping subproblems, we use DP, dynamic programming. Edit one string to another, edit distance DP. Continuous segment substring DP. Similarly, we can see when we talk about suffixes, suffix tree, rolling hash, we see in Rabin-Karp as it uses the concept of hashing. Matches pattern efficiently. Then we use Knuth-Morris-Pratt. And then is a subsequence where you use longest common subsequence. Now we'll start with dynamic programming. In this, we'll solve different types of problems. First is Fibonacci style, where we have to find the nth Fibonacci climbing stairs or ways to reach the top. Now in Fibonacci, we write the final line in a function return Fibo of n minus 1 plus Fibo of n minus 2. That is, if we want the second 20th one, Fibo of 19 plus Fibo of 18 will be equal to your Fibo of 20. The similar concept is applied in case of dp, that dp of I minus 1 plus dp of I minus 2 will be equal to your dp of I. Next is 0-1 knapsack. In zero, there is two types of problems, 0-1 knapsack or fractional knapsack. In 0-1 knapsack, like we had done earlier, 0-1 means either take it or you leave it. You can't take parts of something. You have to take the entire thing together or take nothing. You choose items with maximum profit under the weight limit provided. Now, here we take maximum of either take or not take. Now, this is the pseudo code. So, for I 1 to n and weight 0 to w, where you have space left, there first you see that value plus that value. Suppose there is a value of negative value, or you can say, though a negative value is not possible, but assuming we should have a value which, when incorporated, satisfies our weight also, and it is increasing or making us closer to our final weight. Suppose we added a weight and we are getting more far away from our required answer, so that will not be optimal. So that's why we are using a maximum function here. And otherwise, you let it remain as it is. Next, type 3 problem, longest common subsequence. In this, you find the longest subsequence common in true strings. Now, in this, we compare two strings. We have to find the longest common subsequence. We'll understand this with the help of an example. Let's say we have a string one that is A, B, C, D, G, H. This is a string one. A, E, D, F, H, R. This is a second string. Now, longest common subsequence will be A, A, D, D, H, H. Can you see these are all are in a sequence A, D, and H. But here you can see E is not there. So A, D, H is your LCS. Then F. F is also not there. R is also not there. But E, D, H is also following the order also. Now next, longest common substring, that is E, B, C, D, G, H, A, E, D, F, H, R. Now here your longest common substring will be only D length one, because we have to check for common consecutive characters. Basically, in case of subsequence, the order matters, characters need not be consecutive. Order matters, but need not be consecutive. That is together. But in case of substring, it must be contiguous. Here you can see in order, after A you have B, after E you have E. Now D, you can only have a single one here. I don't think so it will be clear. So let's take another example. Let's say A, B, C, D, E, A, B, F, C. Longest common subsequence A, B. Then after A, B, we have C. We have C. Then we have E. So your LCS will be A, B, C, E. Your length will be 4. Now in case of longest common substring, here it will be AB. They are consecutive in nature also. That's why. So this is the difference basically. Now in form of recurrence, let's see if your S1 of I, in this it will be J. If they both are equal, then I add 1. Otherwise, I take the maximum of the values to the top or the left. Here we are basically, I'll write it. In case of type 3, if it is equal, we are taking it from the previous index, the value plus 1. Now else, if there is no match, then we can't extend. Therefore, we carry over the best result. That is maximum. Maximum or best result. So far, by either ignoring, we are ignoring either the character of S1, ignore current character of S1 or S2. So this is basically what is done in case of type 3 recurrence equations. Now in case of type 4, longest common substring. Now if they are equal, that means they match and they can be a potential substring. Therefore we add 1 to the previous diagonal value. So we'll write previous diagonal value plus 1. Else, since the continuity is now broken, so the substring will have gaps. That is not possible. Therefore, we take it as 0. 0 is basically showing that there is no formation of a substring that is taking place. Now edit distance. In edit distance, we convert one string into another by using insert, delete or replace operations. Now if it is same, we replace it with the previous index value. Then if the characters don't match, you must perform one operation. Now you have three neighbors in the DP table. You have to pick the cheapest one. That is, we use the minimum operation here. Now in case of insert, we'll write dp of I j minus 1. In case of delete, we write dp of I minus 1 is to j. And in replace, we write dp of I minus 1, j minus 1 because we have to move to the previous value. In case of replace, because you are replacing the value. So now your current will change. Now this is your condition for match. This is for we change basically the A of I to B of J. 1 plus is done here, so we'll not do that in every step. In delete, we remove the A of I and move to the next character. Similarly, in insert, we add a B of J to A and move to the next character. Explained here. Now, this is one practice question. You have been given two integers and you are desired to find the length of the longest common increasing subsequence. You are given A and B and you have to propose a dynamic programming based scheme. So I hope now you will be able to solve this question using the pseudo code that I have provided. Next comes your matrix chain multiplication. That is, we need the minimum multiplication cost. Here we use the concept of splitting at k, where dp of I of j will be your minimum over k. We are trying the minimum multiplication cost, like in case of UCS, minimum cost to reach the destination. Now, coin change problem. In this, we are trying to find the minimum coins. Now, first dp of I. We will check if it is minimum of the value or 1 plus the other. I'll explain it using an example. Let's say for an amount I, you check if taking one coin and then let's suppose we take one coin that is fulfilling I, that will be your dp of I, or we take the remaining amount. First will be your dp of I, that is 1 here, plus your remaining amount, which is this going to get us a fewer number of coins. This is what we are checking. We are checking if the remaining amount can be obtained with fewer coins or not. Now, in case of count ways, you obtain the find the total number of combinations that sum up to the target amount. Now, the number of ways to reach the amount I will be equal to the sum of ways to reach I minus coin. That is your previous state. You are basically carrying over the possibility of smaller to the current one. That is your bigger amount. Now, in case of longest increasing subsequence, here we use the concept of DP, where we are checking for j less than I. If this condition is fulfilled, we take maximum of dp of I or dp of j plus 1. For every index I, we look at a previous element j. Now, dp of I is 1 because the single number is a similar increasing subsequence only. Then after that we are checking if it means the current number can be appended to the subsequence ending at ARR of j. If it is less, now we update the current dp value to the maximum length found. In this case, it will take order of n square. Now, in case of type 9, that is palindrome dp, you take the longest palindrome subsequence. Let's say your s of I is just to j. Now, if your s of I equal to s of j, and second, the inner substring is also a palindrome. That is dp of I plus 1 j minus 1 is true. That is, it is a palindrome. Then you return it as true. This is what is in type 9. Then type 10 is your partition. In partition, like rod cutting and burst balloons, you solve your left part and right part. This we have done in a concept known as divide and conquer. Next is the string algorithms. In case of string algorithms, we have naive pattern matching, which takes order of nm time complexity, and you compare your pattern with text one by one. Newt Morris Pratt, very important. It is used for efficient pattern matching and using a LPS array. Now, how do we create an LPS array? Let's understand that. Now, I have first taken an example of AAB. Now, A has no proper prefix. Now, proper prefix means not containing the string itself. Now, A has no proper prefix, so value will be 0. Now, AA, suffix is A and AA. Your proper prefix are A only. So, is it matching to your suffix? Yes. Only one value is matching, value is 1. AAB. Your suffix we have A, B, AB, AAB. Your proper prefix A, then double A. So only I think so A is there. This is your B, double A, not there. So value will be your proper prefix is not matching with your suffix. So in this case, your proper prefix is equal to suffix count is taken care about. Now in the pseudocode, what we are doing is if we have a text and a pattern, we try to move both the pointers. Now if your pattern is found, pattern found, you look for its next occurrence. And if there is a mismatch, then you don't reset I. Reset I. You just move your J back to LPS of J minus 1. This part is very important. And you simply go to I plus plus. This question is very important. Newth-Morris-Pratt is mostly asked as a question to solve. Not mostly pseudocode is not asked. So do practice this question. Next is your Rabin-Karp, which uses the concept of hashing or rolling hash. It compares hash first, old hash minus leading into base plus tree. We'll understand this with the help of example. Then last is your Moore. It compares from the right hand side, bad character heuristic and usually theoretical. As you have seen in your classes where you had drawn NFAs in TOC, theory of computation, like A, B. Now, in case you have A, you go back. In case you have B, you go back. In case you have A, you go back. This is your final state, and this is your initial state. Now, super important trick, like we had done in the table, that was the first slide. Best, minimum, maximum count ways. What will we refer to? DP. Find button, match text, or search substring. String algo. If this all suffix repeated substring, think of a suffix tree. Let's start with the first question. We form a recurrence equation and solve it using a master's theorem. Now, in this question, we have to use the form T of n by b plus fn. Now, in this case, your function is returning log n and root 2 a n by 2. Now, basically, your a is your number of subproblems that will be equal to root 2 a n by 2. Like it will be like root 2 a n by 2, which we obtain from here. Now, I'll write here number of subproblems. Now, b will be 2. Why? Factor by which n is divided. Here we can see 2. Then f of n, your function, work done outside your recursion. This we can see log n from here. So you form your equation. Now when you have found your equation, you calculate n log b of a. This will be n to the power log 2 of root 2. This comes out to be n to the power 1 by 2. That is root n. Now in case of comparison between log n and under root n, we know that log n will grow much slower than root n. Why? Let's see. Log n is equal to order of n.5 minus epsilon. That is the reason. For any epsilon greater than 0. This fits your case 1 of Master's theorem, by which we can say when fn is less than your n log b of a, you say that your a of n is equal to order of n log b of a, that is order of root n. This matches the answer here. So these were the steps involved. Now let's read this question. Given two substrings, one string, the second string, use the maximum length of subsequence as well as the resultant subsequence present. Use memorization technique. We'll see this question in the next slide. So you have given basically two strings A, B, A, A, B, A, B, A, B, B, A, B. Find the maximum length of subsequence. Maximum length of subsequence as well as the resultant subsequence. Use memorization technique. This question is basically about your longest, so longest common subsequence. Now here we have to use memorization, that is dynamic programming. It is hinting that you have to use dynamic programming approach. Now in case if your match is found, this case is showing if your match is found. If the characters match, you take the value of the diagonal top cell and add one. Diagonal top cell. Otherwise, if it is not equal, then you take the maximum of the cell I had explained. Let's take this example. Suppose this is your x, y, and z. To fill x, you'll take the maximum out of y and z. That is your left side and your up. In this case, now when the string is null, you know the values will be 0, you fit 0 in all the cells. I'll explain it. Now after that, A, B, is it matching? No. So what we'll do is, we'll take the maximum of left and right. Preference given to left, preference to left. So you write 0 and draw the arrow. Arrow is drawn towards the side that you have given preference to. Now A from here and A from here. You go to this cell. It's a match. That means 1 plus the diagonal value here. That is 0 plus 1, 1. Arrow goes to the 0 where you've taken the value from. Next, A, B not matching. So value, maximum value of left and top is 1. So 1 comes here, arrows drawn, arrow drawn. And similarly, when you'll complete this, you will reach to your answer of. Now length of your commons, longest common subsequence will be 4. And the sequence will be BABA, B-A-B-A. How? Let's see the movement with the help of a yellow pen. So 4, 4, 3, 2, 2, 1. We have to see where a value is increasing due to a match. So this 4 will go here, then your value increase from here, then your value goes here. This point to your left, this points here, points here. So B A B A. Now basically you start at the bottom right. So you found the letter A, then you moved diagonally up. You found a letter B. You here moved up. You found B. Then after that, it matches at A at this position where it's moving diagonally up. I hope you are able to see. So you get A. Then after that, when you go up here, do you get a match? No. So we move up. Here do we get a match? Yes. See, here we get a match. So we take this one. So BA, BA. So understand, you have to only take the match ones. Match ones. Here we saw where we are moving diagonally up. That means we have to select those ones only because those are fulfilling a first if condition. Now next question. I think so. This question may not be visible. So I'll read the question. A multinational company has two data centers located in Bangalore and Hyderabad. The network between these data centers is represented using a weighted graph. Each edge weight denotes the maximum bandwidth capacity of that communication link in Mbps. A data transmission path starts from a server in Bangalore and ends at Hyderabad. The capacity is defined as minimum bandwidth edge because the slowest connection determines the overall transfer speed. Design an efficient algorithm to determine the path to provide the maximum data transfer. This is known as the maximum capacity path problem. In this, it is not to minimize the distance but to maximize the minimum bandwidth. Since smallest edge capacity determines final transfer rate, therefore we need to find a path where the bottleneck edge is as large as possible. Here we use the Dijkstra's algorithm. In the normal Dijkstra, the shortest distance of every node is maintained instead of storing the minimum distance. Here also let's understand with the help of example. We have one path from Bengaluru to Ahmedabad and these are the capacities 10, 8, 6. Overall becomes the smallest 6 Mbps because the smallest limits the transfer speed. If we provide another path 9, 9, 7, then overall will be 7 which is better. So the second path is selected. The algorithm will continue until all reachable nodes are processed. Here we know we have to get the maximum possible transfer capacity. The time complexity will be edge of log of vertices. The algorithm is correct because at every step it chooses the node which is currently maximum achievable bandwidth, like we have seen with the help of example. Try to understand every concept with the help of example because then only your concepts will be clear. Next, apply cost-effective algorithm to give pattern from text. I had told in the earlier trick slide, whenever we say efficient or cost-effective, we use KMP, Newt Morris Pratt. Now in Newt Morris Pratt, we are given the text and the pattern. Now first iteration, you take O matches, N matches, I matches, O, N. Then there's a mismatch. Mismatch at the fifth position. You start the search from the index value 2. We had done LPS. In LPS, what we are doing is we are checking one by one. When we take O and O, no match. O and N, O, N, I, O. First, we'll check this one. So your prefix will be O, O, N, O, N, I. This is a proper prefix. Your suffix will be O, I, O, N, I, O, O, N, I, O. O and O matches. O, N, not there. O, N, I, not there. So, one match. Then you take O, N, I, O, N. So your proper prefix are O, O, N, O, N, I, O, N, I, O. Your suffix will be N, O, N, I, O, N, N, I, O, N. This is not matching, this is not matching. O, N is matching. So here, your value will be 2. I hope you have understand the concept. Here, your string that we got in proper prefix and your suffix had a length of 1. Here it is having a length of 2. That's why we get 1 and 2. Now similarly, after this, when we have got a match, after the first mismatch, that is after the sixth character, that is fifth index, now the text has I, but the pattern needs a S. Yeah, I and S. Instead of restarting, now we go to LPS of J minus 1. That is LPS of 5 minus 1 is equal to LPS of 4, which is basically your 2. This tells us that the last two letters matched are also part of our pattern, that is ON. Now after this, the pattern has shifted so that its first two letters align with the ON at the end of the previous match. We have found a match here, but now the second and the third iteration is seen. Now, when we see here IO, there's a mismatch. When there's a mismatch, now a full match of the text will be starting at index of 3, ONI1, S. So basically the comparison will resume against the third letter. Now LPS of 2 minus 1 will be LPS of, now LPS of 2 minus 1 is 0. So now you start from your 0th position. Now when you come, you move to I plus plus now. You are moving one by one. Now you have gone starting from your fourth letter now. In fourth letter, you find all are matching. Your index positions also, so your length is basically 3. Like you have seen, we have started moving here. Like we found OM, we moved by the step of 2. This is our value. Then here also we moved by one position. Like in the case of second one, now LPS of the first character is always 0, as we all know. So because there is this 0 overlap, so now it has no choice but to move forward by 1. 0, in the case of 0, it has no choice but to move by 1. But here we had 2. So we moved by 2 spots, and this is how we find the pattern. This is a very important question from your exam point of view. Satisfiability, 0-1 knapsack, longest path problems have something in common. If any one of them can be solved in polynomial time, then all others can be solved in polynomial time. Explain the relationship. Now, these are both NP complete problems and are related to each other through their polynomial time reduction. One problem can be converted to another in the polynomial time. Now, this SAT problem checks whether a Boolean formula can be made true by assigning values to a variable. The 0-1 knapsack checks whether the subset of items can be selected for a given capacity with the required profit. It can be transformed in polynomial time. The variable and clauses are represented as items, weights and profits in the knapsack problem. Basically, what they are trying to say, the variables and clauses are basically the item, weight, and profit we see in the knapsack problem. Thus, this is the relation. Therefore, we can say a polynomial time solution exists for 0-1 knapsack. Then SAT can also be solved in polynomial time. Since SAT is NP complete, they would be they would become polynomial time solvable. Thus, all these problems are related and solving one efficiently can help solve others. Next question. A string is stored in a suffix array. A pattern is required to be searched on the string. Write all intermediate steps for finding the offset at which the pattern is found. Floor function can be used while calculating the value of mid. Now here basically we use the concept of a suffix array. Now length of string 1 is 7. Now a suffix array is basically a list of the starting positions of all possible suffix. Start position of suffix in alphabetic order. So 6, index 0 means this, then index 1, then 2, and similarly till index number 6. So therefore we just 6, 5, 4, 3, 2, 1 because it is a suffix array. Now we start with the binary search part. Similarly, length of 2 is 6, low is high, low is 0, high is maximum of L1 and N2. That is, of course, your L1 because that will be a string, not the pattern. Maximum will be a pattern, otherwise, your string pattern will ever be able to match the string. I mean to say that your text should always be greater than your pattern or equal to match it. Now we want to find a pattern in the sorted list, so we start in the middle and then narrow it down. So in case of mid, we use the for function and got 3. Now is our pattern bigger or smaller than AAA? Since our text is longer, so it is bigger alphabetically. Now ignore everything at index 3. Now ignore and search your top half. Now the suffix at index of 5. This will give you an exact match. Here like we found 3. And first then we use floor here. 0 plus 7 by 2 and then we got 3. Then after that we update our range. When p is greater than your suffix, we move to your right half. Low will be equal to mid plus 1 is equal to 4 and high will be equal to 6. Calculate this will be in the first case low 0 high 6. In the second case we'll have low as mid plus 1 and high as 6. Then when we calculate mid as floor of 4 plus 6 by 2, we get a value of 5. Now this 5, retrieve SA of 5. This is what this is the meaning of getting 5. Now S of 1 is to 5 will be equal to your, we are basically retrieving a suffix here. And we get the exact pattern. At mid is equal to 5. Thus the pattern is solved at offset 1 in the original string. Next, categorize the following under P, NP hard, NP complete. Vertex cover is a NP complete problem as it is a decision problem and it is also NP hard because SAT can be reduced to vertex cover in polynomial type. NP complete M coloring. Checks if a valid coloring is easy, but finding a valid coloring with M colors is NP hard due to combinatorial explosion, because there could be n number of combinations that we can test. Binary search. It runs in logarithmic time, which is polynomial time. So basically class P. Next, this is a question of DP, where we have done matrix chain multiplication. We have many options to multiply a chain of matrices, but we have one method, that is matrix multiplication. In other words, no matter how we parenthesize the product, the result will be same. However, if we change the order in which we parenthesize the product, the number of operations may compute may also change. It is desired to solve the problem using a dynamic programming approach. Now you have to solve this using a TP based approach. Here you take minimum number of scalar multiplications needed to multiply. Your recurrence will be minimum over k that we had talked about, that is dp of I of k plus 1 to j, and plus your cost associated. Here first we'll check base case will be if I is equal to j, that is we are looking into a single matrix. So therefore no multiplication needed. Now in case of this, first of all, the first part is basically for your multiplying your first subchain. This is for your second subchain. And this cost basically is your when you multiply the two resulting matrices I minus 1, k and j. Now we are given A1, A2, A3, A4, A5. We have to check for the optimal split. 4, 3, 5, 1, 8, 2. So you have to find for the optimal grouping and the minimum number of multiplications. So basically the optimal combination here will be A2 into A3 and into you can say A4 into A5. Now here basically 27 on the left side plus 16 to the right and 8 for your final combination. You get a total of 51. In case of A2 into A3, this part you'll have 3 into 5 into 1. So here you get a resultant of 3 into 1. Then A1 into this whole part. 15 plus 4 into 3 into 1 is equal to 27. Your result will be a 4 cross 1 matrix. This was equal to your 15. Then next A4 into A5, this will lead to 1 into 8 into 2 is equal to 16. 1 into 2. Now final will be basically 4 into 1 into 2, 8. So this is what we have done. Let's see the steps written properly. First, we'll check the cost calculation of A1 into A2. We check the second combination, the third, and the fourth. We compute the total cost. Like first you have to take individual brackets and then take the brackets along with the expression and calculate. I had explained about the recurrence equation. I hope you will be able to solve for the minimum number of multiplications. Now, when solving in exams, you always multiply the smallest middle dimension first. 5 into 1, 8 into 2 is good. Avoid big intermediate matrices. Reduce change step by step. Don't jump randomly. Always shrink the matrix sizes. Write cost immediately after each multiplication. Next, it is desired to search numerous patterns in a text. We may store the text T into a suffix tree or into a suffix array and search for the desired pattern. Now we have to check for space and time complexity. The suffix tree and suffix array are both used for efficient pattern searching, but they differ in space and implementation complexity. Your suffix tree is very fast pattern searching in linear time. It requires very high memory due to pointer-based structure and complex to construct and maintain. Suffix array is space efficient and stores all suffixes in sorted order. Much less memory, easier to implement, m log n, time complexity. Therefore, we are preferring a suffix array, less memory, and also we are able to solve in binary search, approximately that time complexity, that is order of n log n. Now first we store all the suffix of t. Then we search this pattern and it is like it is found in suppose index 3, 0, 1, 2, 3. We found this ABB. Is it there? No exact match, therefore not present and not present. Next, now we sort suffix using the lexicographically. Here 3, 0, 1, 4. Now you store them in a suffix array. Now you use pattern search using your essay. We use binary search basically on a sorted suffixes. So AABCB, AABCB found, ABB not found, ABAA not found. This is the way you have to solve in your exams. You have to write these steps and then solve. It is desired to find two patterns in a given text. Pattern 1, pattern 2. Propose an efficient strategy in which T is scanned only once and to search the occurrence of both of them together. Here we'll use the concept of a try. Here both patterns are inserted into a try. The failure links ensure whether when a mismatch occurs, the algorithm does not restart from the root, but transitions to the longest possible valid prefix. It is scanned once and detected efficiently in your linear time. N plus total pattern length and n number of nodes in the try. Now, these are the tables summarizing what all we have done today. We have done Naive, KMP, Rabin-Karp, Z we have not done, and Moore. Then we saw different types of problems based on dynamic programming. Then after that, we did the concept of a suffix tree, suffix array, and a question on this algorithm. So thank you all. This was all for today's video. Here we covered different concepts of DAA. If you have any doubt, do mention them in the comment section. I'll be answering them. So if you like the video, do like, share, comment, and subscribe to my YouTube channel. So okay, tada, bye bye.